We shall see some important applications of electrolytic cells in detail. The electrolytic cells are used in extraction of the metals from their fused salts. The electropositive metals such as sodium, potassium, magnesium, etc. are extracted from their respective matter or salts in their fused state. Sodium is extracted by the electrolysis of fused NaCl. In this electrolysis, NaCl is taken as electrolyte which undergoes dissociation on sending current to give Na plus and Cl minus ions. On passing current, the anions, the Cl minus ions are coming towards anode and undergo oxidation to give chlorine gas, which is obtained as byproduct. Meanwhile, the sodium plus ions undergo reduction at cathode to give sodium. Sodium is deposited on cathode, which is taken out from time to time from the cell. Similarly, in the electrolysis of fused magnesium chloride, magnesium is obtained at cathode. The second application of electrolysis is electrolytic refining. Many metals such as lead, copper, aluminum, etc. are refined by electrolysis. In electrolytic refining, always the impure metal which is to be purified is taken as anode and some pure metal is taken as cathode. These two electrodes are immersed in a solution in which the metal ion is present. The two electrodes are connected to high voltage battery. When current is passed into this solution, always the anode metal undergoes oxidation and the ions of this metal are dissolving and go into solution. As more and more ions are formed, the ions are going towards cathode where the cations take electrons which are coming from the circuit, and we can see deposition of a pure metal on cathode surface. The reactions taking place in electrolytic refining of copper can be shown as the impure anode copper undergoes oxidation to give copper 2 plus ions and electrons are moving through circuit. Copper ions are coming into solution. The copper 2 plus ions undergo reduction at cathode to give pure copper, which can be written as copper 2 plus 2 gives rise to copper. Pure copper is deposited on cathode. The impurities present in the anode are falling as anode mud at the end of the electrolysis. The next application of electrolysis is electroplating. The process of depositing one metal over the other metal by means of electrolysis is known as electroplating. Electroplating is used generally for decoration purposes, picture frames, ornaments, etc. For prevention of corrosion also electroplating is used. Generally, iron is electroplated with chromium or nickel to prevent rusting. Electroplating is an application of refining of the metal. In electroplating, the article to be plated is always taken as cathode. For example, in this electrolytic cell, a spoon is taken as an article to be plated by some other metal and it is taken as cathode. This is kept in electrolytic cell. The electrolytic cell used for electroplating is consisting of a rectangular steel tank in which the article to be plated by some other metal is taken always as cathode. The metal which depositing on this article is taken as anode. These two electrodes are kept in a solution whose ion is coming from the anode after oxidation. When the two electrodes are connected to high voltage battery, the anode undergoes oxidation and gives ions. As more and more ions are formed, they are coming towards cathode, that is article, and the ions are getting deposited as metal on the spoon. In case of electroplating of silver, silver is taken as anode, silver nitrate is taken as electrolyte, and an article such as a spoon is taken as cathode. When the two electrodes are connected to high voltage battery, the silver from anode undergoes oxidation and gives rise to silver ions. As more and more ions are formed, they come towards cathode and get deposited as a deposit or as a layer on the spoon. Silver nitrate is undergoing dissociation to give Ag plus and NO3 minus. At cathode, that is on the spoon, the Ag plus ions are deposited as silver by taking electrons. The silver present in the anode is reacting with anions of AgNO3 and giving rise to AgNO3. That is, the silver of the anode is undergoing dissolution in the form of AgNO3. At the end of the electrolysis, silver is deposited on the spoon. After getting deposit on the spoon looks like as shown here. The other application of electrolysis is electrotyping. It is an application of electroplating. It is used for preparation of blocks for printing purpose. The impressions of various letters or numbers are required for printing or obtained either on wax or plaster of Paris. These engraved blocks of wax or plaster of Paris are coated with graphite or lead. To make them conductor, they are coated with graphite. It is made as cathode in an electrolyte such as acidified copper sulfate solution. Pure copper is taken as anode. On passing current, copper deposits on these impressions. Then the wax is removed from these copper impressions. The galvanic cells are those in which the chemical energy present in the chemicals is converted to electrical energy. In these cells always we are driving the reaction in a direction in which the reaction is spontaneous, so that an unstable compound is converted to a stable substance, and stable substance is having less energy. Therefore, the difference of energy between the reactants and products is converted to electrical energy. Hence, these cells are used to generate electrical energy in minute quantities. Hence, galvanic cells are used to transport current from one to other place, and thereby they are highly useful in our daily life. For example, we cannot carry current always from one to other place in a particular system. Suppose you are traveling a car and we need to run some system by using power, and this power in car is generated by using lead storage battery, which is an example of galvanic cell. Similarly, many other things which are seen or which are used in our daily life are being run by the cells which are galvanic cells, such as the cells present in wristwatches. The dry cell batteries are examples of this one. Once again, in galvanic cell, the reaction taking place is spontaneous, whereby an unstable compound is coming to a stable compound. Hence, we see production of current. In this cell, always the electrons are flowing from anode to cathode, but in terms of charges, the electrons are flowing from the negative electrode to positive electrode. In galvanic cell also, the reaction taking place is a redox reaction or electron transfer reaction. Here also we see oxidation at anode and reduction at cathode. The EMF of the galvanic cell is always positive. The galvanic cells are also known as electrochemical cells. Dry cell battery, dead storage battery are examples of galvanic cells. A simple galvanic cell can be shown as shown in the diagram. It is consisting of two compartments. One compartment, the first compartment is for example filled with 1 m zinc sulfate solution with zinc rod in that. The second compartment is filled with aqueous copper sulfate solution of 1 m concentration with copper rod in it. The two cells are having a U-shaped tube as shown in the diagram, which is known as salt bridge. The salt bridge is generally consisting of KCl in agar-agar. The two rods, that is zinc and copper rods, are connected to each other using a bulb and voltmeter in the circuit. Remember, in this circuit no external battery is used. When the two metal rods, which are now known as electrodes, are connected to each other, we can see a spontaneous glow of the bulb, indicating the flow of the current from one to other end. The EMF with which the current is flowing from one to other end can also be read from the voltmeter. In this experiment, it is found to be 1.1 volts. As shown here, when the two metal rods, copper and zinc rods, are connected to each other, the bulb is glowing, indicating the flow of the current from one end to other end. To understand which one of these two electrodes are acting as anode and cathode, we have to see the reactions taking place in these two compartments. In the first compartment, it is seen that the zinc rod present in the solution is undergoing oxidation and giving rise to zinc 2 plus and 2 electrons. The electrons are coming out through circuit and they are entering into the second compartment. The electrons are taken by copper ions in the second compartment and copper is deposited on the copper. It is also seen that these two reactions are also seen from the decrease in weight of the copper and increase in weight of the copper sheet in cathode compartment. The overall reaction taking place in the cell can be shown as zinc plus copper 2 plus giving rise to copper 2 plus plus copper. Above scheme is indicating that zinc is acting as anode because we see oxidation there, and copper is acting as cathode because copper ions are undergoing reduction. In other words, zinc is supplying electrons and hence acting as anode, and because of supplying of electrons, zinc is said to be having negative charge. Therefore, anode of the galvanic cell is having negative charge. The copper ions are taking electrons from the copper metal. Therefore, copper is acting as cathode and it is having positive charge. The voltage difference through which current is flowing from one to other end is known as EMF of the cell. It is measurable using the voltmeter. The salt bridge present in the circuit, which is consisting of KCl in agar-agar, is helping in maintaining electroneutrality of the solutions. The EMF of a galvanic cell, which is abbreviated as E cell, can also be calculated by the following equation. E cell is equal to oxidation potential of anode minus oxidation potential of cathode. The second equation, E cell is equal to reduction potential of cathode minus reduction potential of anode. The third equation, E cell is equal to oxidation potential of anode plus reduction potential of cathode. We shall see now the representation of the galvanic cell on paper, which is known as a notation of the galvanic cell. Before that, we shall also see the representation of the electrodes of the galvanic cell. In anode, a metal undergoes oxidation to give M plus ion. Therefore, this anode is represented as a M oblique M plus. For example, when zinc is present in zinc sulfate solution, if a zinc is acting as anode and undergoing oxidation, the representation of this is zinc oblique zinc 2 plus in terms of ions, or zinc oblique ZnSO4 in terms of molecules. Similarly, in cathode we see reduction reaction, that is the M plus ion present in the cathode compartment undergoes reduction by taking electrons and getting converted to M, that is metal. Therefore, the representation of the cathode is M plus oblique M. If a copper is taken as a electrode in the galvanic cell which undergoes reduction, the representation of copper is copper 2 plus oblique copper in terms of ions, or copper sulfate oblique copper in terms of molecules. When these two electrodes are combined to form a galvanic cell, the representation of this can be shown as M plus oblique M X plus oblique X. That means the anode is always shown first in the cell notation, followed by cathode. Between these two, the double oblique is representing salt bridge. If the earlier galvanic cell consisting of zinc and copper electrodes is taken, wherein zinc is undergoing oxidation and copper is undergoing reduction, the representation of this can be shown as zinc oblique zinc 2 plus double oblique copper 2 plus oblique copper. The concentrations of the ions present in the solution are also shown beside the ions. We can also represent the cell notation in the form of molecules or molarities as shown here. Zinc oblique zinc ZnSO4 double oblique copper sulfate oblique copper. In the earlier galvanic cell which is taken as example with the zinc and copper electrodes, we have seen zinc is acting as anode and undergoing oxidation, and copper is acting as anode and copper is acting as cathode and undergoing reduction. Why zinc undergoes oxidation, why not reduction, and why copper undergoes reduction, why not oxidation, is explained by the term known as electrode potential or single electrode potential. When any metal is present in solution of its own ion, such as the first or second diagram, we can have two possibilities. One is the metal atoms present in the metal can undergo oxidation to give corresponding ion. We can consider the forward reaction. Or the other possibility is the ions present in the solution can take electrons and getting converted to the corresponding metal. Both the forward and backward reactions are possible. Which reaction is taking place is depending upon the type of the other electrode present in the galvanic cell. For example, when a metal is losing electrons as shown in the forward reaction and giving ions, the metal is said to be undergoing oxidation. This tendency of the metal to lose electrons like this is known as oxidation potential. Similarly, if the metal ion is taking electrons and getting converted to metal atom, this tendency of the electrode to take electron and undergo reduction is known as reduction potential. The tendency of an electrode to lose electrons and undergo oxidation is known as oxidation potential. The reaction can be shown as zinc gives rise to zinc 2 plus 2 electrons in case of zinc electrode. Similarly, the tendency of an electrode to gain electrons and undergo reduction is known as reduction potential. A corresponding reaction is copper 2 plus 2E gives rise to copper. The oxidation potential of zinc, for example, is 0.763 volts. Similarly, the reduction potential of copper is 0.337 volts. These values are obtained by some other experiment. For a given electrode, the oxidation potential can be converted into reduction potential, or reduction potential can be converted to oxidation potential by using the two equations. The electrode potentials are expressed in volts. Though we can define electrode potentials as given earlier, the electrode potentials are depending upon several factors such as temperature, nature of the electrode, the concentration of the ions in solution. Hence, the simple electrode potentials are not useful to say which metal undergoes oxidation or reduction when the two metals are present in galvanic cell. For this purpose, we define one more term which is more useful, known as a standard electrode potentials. When a metal is present in a solution of its own ion of 1 m concentration at 25 degrees centigrade and a pressure of 1 atmosphere, in case of gas, the electrode is said to be in standard state. Now, the standard oxidation potential is simply the oxidation potential of the electrode in standard state. Similarly, the standard reduction potential of the metal is the reduction potential of the electrode in standard state. The actual definitions of these two can be given as the tendency of the electrode to lose electrons and undergo oxidation in standard state is known as standard oxidation potential. It is abbreviated as SOP. Similarly, the tendency of the electrode to gain electrons or to undergo reduction in the standard state is known as standard reduction potential, which is abbreviated as SRP. The notation for standard oxidation potential is E0 ox. 0 is shown as superscript and ox is shown as subscript, or E0 m oblique m plus when a metal is present in solution of its own ion of m plus. The notation for standard oxidation potential of zinc is E0 zinc oblique zinc 2 plus. The standard oxidation potential of zinc is 0.763 volts. Similarly, the notation for standard reduction potential is E0 RED. 0 is shown as a superscript and RED is shown as subscript. Similarly, when a metal M is present in solution of its own ion of M plus and undergoing reduction, then the notation for standard reduction potential is E0 M plus oblique M. The notation for standard reduction potential of copper can be shown as shown here. The standard oxidation potential can be converted into standard reduction potential by the following equation. That is, the standard oxidation potential of an electrode is equal to minus of the standard reduction potential. Similarly, the standard reduction potential of an electrode is equal to minus of the standard oxidation potential. The standard potentials of electrodes are determined by using standard hydrogen electrode, the abbreviation of which is SHE. The standard hydrogen electrode is also known as the normal hydrogen electrode, abbreviation of which is NHE. This electrode is taken as a reference one to measure the standard electrode potentials by taking the electrodes in standard condition. The construction of the standard electrode potential can be shown as here. It is consisting of one rectangular tank which is having a 1 H plus ion solution such as hydrochloric acid. It is having a tube as shown here, inside of which a platinum rod is present. At the other end of the platinum rod, a platinum plate is taken. From upper part of this glass tube, hydrogen gas is sent at a pressure of 1 atmosphere and at a temperature of 25 degrees centigrade. Therefore, this is said to be in standard condition. When hydrogen gas is sent into a solution of 1 H plus ion at a pressure of 1 atmosphere and a temperature of 25 degrees centigrade, the oxidation potential of this electrode is taken as 0 by definition. Therefore, the oxidation potential of hydrogen electrode is equal to 0. Similarly, the reduction potential of the electrode is also equal to 0. The standard electrode potentials are determined by using the standard hydrogen electrode. If the standard reduction potential of a given electrode is negative, it is having more tendency to undergo oxidation compared to that of hydrogen electrode. Similarly, if the standard reduction potential of a given electrode is positive, it is said to be having more tendency to undergo reduction or less tendency to undergo oxidation compared to that of hydrogen. After determination of the standard electrode potentials of the electrodes are arranged in a decreasing order of the standard oxidation potentials or increasing order of the standard reduction potentials. In such case, we get one series which is known as electrochemical series. This is the electrochemical series in which the electrodes are arranged in increasing order of the standard reduction potentials or decreasing order of the standard oxidation potentials. We shall see several significances of the electrochemical series. One is when two metals are present in a galvanic cell, which metal undergoes oxidation or reduction can be known by the values or the position of the metal in electrochemical series. For example, a metal of the electrochemical series can reduce any ion present below it. For example, lithium can reduce potassium ion or calcium ion or sodium ion or magnesium ion when that is present in galvanic cell. Therefore, lithium always acts as anode and all others which are present below it are acting as cathode in the galvanic cell. The second use is the metal present in a galvanic cell can oxidize all others present above it. For example, you take zinc. The zinc ion can take electrons from aluminum or magnesium or sodium metals, but a zinc ion cannot take electrons from iron or tin or lead when they are present in galvanic cell. Hence, zinc is acting as a anode when it is present along with these metals, and zinc is acting as cathode when that is present along with the metals which are present above it. The third use of the electrochemical series is using the standard reduction potentials which are given here. The EMF of the galvanic cell can also be calculated without going for experiment.
Further clarification, contact the Additional Secretary, State Board of Technical Education and Training, 7th floor, BRKR Bhavan, Tank Bund Road, Hyderabad 500063. Fax 040 322 0546.